actually going to another question of 2018, and this is the question number 14. The question number 14 states the activation energy, the EA values for two reactions carried out at 25 degrees Celsius differ by 5 kilojoule per mole. If the pre-exponential factors, that is the A1 and A2 for these two reactions are of the same magnitude, the ratio of rate constants, that is K1 divided by K2 is, and they have also said to round up the value to two decimal places, and they have given the gas constant value, that is 8.314 joule Kelvin inverse and mole inverse. So now let us here you are seeing a term known as the activation energy. So first you need to know that what is an activation energy. So the rate, we have just talked about that how the what is the rate of a chemical reaction. So the basic idea is the reactant is getting converted into a product. So this is the criteria for performing for undergoing this reactant to convert into a product and undergo this chemical reaction faces a energy barrier. Which is this energy barrier? And this is known as the activation energy. So this is a transition state through which every reactant have to go through to convert into its product, and the energy which is required for reaching from the reactant to the transition state is the activation energy. So the more the activation energy, the lower is the rate constant. Why this is so? Because if the activation energy is more, then the reaction will be slower. It requires higher energy to overcome this barrier, that is this barrier that you see in red line, to convert into the product. That's why if activation energy is more, than your rate constant is lower. Okay, so now this rate constants or the equilibrium constants, they all depend upon the temperature. Okay, so they vary with temperature. So here so the relationship between this rate with the temperature is given by Arrhenius equation. So this equation will be very helpful for us if for solving the question that we have just discussed. So Arrhenius equation implies that the rate constant, this is the rate constant that you see here. So the rate constant of a reaction increases exponentially when the activation energy decreases. When the activation energy decreases, the rate constant increases exponentially. So this is the equation where this K is your rate constant, A is the frequency factor, or it is also called as the pre-exponential factor, which determines that how many molecules or what fraction of molecules will actually interact with one another to form the product. So that frequency is the frequency factor, or the under a means this means A is the also known as the frequency factor or the pre-exponential factor. Now this small e is the exponential component, that is the E, and also this minus EA by RT. EA is the activation energy, T is the absolute temperature or the Kelvin temperature, and R is the gas constant. So this is the way which we can calculate the rate constant with the help of these parameters, and this is the relationship between a rate constant and the temperature, which is given by Arrhenius equation. Now this is the Arrhenius equation that we have. Now if we take logarithm in both the sides, then it is coming as ln k equal to ln A minus EA by RT. So just a mathematical trick we are doing here. We are adding both sides. We are taking a logarithm in both sides, ln. Okay, now we again know that ln is the base is e here, but in log the base is 10. So if we want to convert ln to logs, so the value we have to multiply is 2.303. Now, if we add this ln value, that is 2.303 log, in this equation, we get 2.303 log k equal to 2.303 log a minus Ea by RT. And finally, this will lead us to this equation. Okay. So this equation is telling us that log a equal to log k equal to log a minus Ea by 2.303 RT. So if you look here minutely, so then you can see here this is your y. Okay, this value is your m x, and this value is your c. So if you see that this equation is coming like y equal to mx plus c, y equal to mx plus c. So then if you plot this y, that is log k or ln k, with the 1 by t where your x here, so this is a revert back, so this is actually this value, and this c is this value. Okay, so so if you see here is that this mx, m is this ea minus ea by 2.303 r, and 1 by t is your x, and the c here is log a. Just you need to rearrange this equation a little bit and you will get this form, y equals to mx plus c. I am repeating here again that this m here is this minus ea by 2.303 r, and x here is 1 by t, and whereas this c value is the log a and the log k is y. Okay, and if you plot ln k with 1 by t, that is y with x, that is 1 by t, you will get a slope, and the slope value, that is the m, is minus ea by 2.303 r. And if you have in ln, so it is only minus ea by r. So from here you can actually calculate the activation energy. Now if you take the Arrhenius equation in two temperatures, that is T1 and T2, then there will be two equations. The first equation is log K1 equals to log A minus Ea by 2.303 RT1. We are considering that A are same for both these two temperatures. So that's why we have not written A1, A2. It is A only. Log K2 value is this. Now if you subtract 2 from 1, that is 2 minus 1, then 1 from 2, then it is coming as this log k2 minus log k1 equal to this, and there is also a plus term. Now if you solve this equation further, then you find this equation, and this is very important for us, that is log k2 by k1 equals to ea by 2.303 r into T2 minus T1, that is the change in temperature, the second temperature minus the first temperature, or final temperatures minus the initial temperature, divided by the product of these two temperatures. Okay, now having this concept of what is an activation energy and how this rate is dependent with temperature, now let us again look back to our question. So the question was stated as the activation energy values of these two reactions. The temperature here is maintained, that is 25 degrees Celsius. They actually their activation energy which is at 25 degrees Celsius, but there are two reactions. So each of the reactions activation energy differed, means the two reactions activation energy differed by 5 kilojoule per mole. Okay, and they have said that for both these reaction there are two pre-exponential factors, so that is a1 and a2. If you remember the Arrhenius equation, so this here we are considering it as a, and so here they have said that this is a1 and a2. For these two reactions are of the same magnitude, they have the same thing, that a1 is here equal to actually a2. So, and also what we need to find here is K1 by K2. So what they have given is that the difference of activation energy between two reactions is given, the temperature is given, the they have mentioned that the pre-exponential factor for both these reactions are same, and what they want us to find out is that the ratio of the rate constants of the two reactions, and they have also mentioned the gas constant. Okay, so what will be the solution? So what they have given, EA is given, the change in EA is given between the two reactions, that is 5 kilojoule per mole. And if we want to convert it into joule, since it is a good practice, joule is the SI unit, so always try to convert all your values into the SI unit. That will make your calculations easy. So 5 into 10 to the power 3 joule per mole. Now from Arrhenius equation that we have just seen, so from Arrhenius equation, so we have two rate constant. K1 is for the first reaction, where it is A1 e to the power minus EA1. That is the activation energy for that reaction divided by R into T. The T is the absolute temperature and it is given to be 25 degrees Celsius, and which is actually 298 Kelvin. K2 is another rate constant for the second reaction. Now it is also given that A1 is equals to A2. Now if we divide this 1 and 2 together, then what we get is K1 by K2 is equal to A1 divided by A2 plus e to the power minus EA1 plus EA2 divided by RT. Just you need to know that when they are exponentially divided, so their coefficient will get subtracted. So in that way the EA2 is getting positive and you are getting this value. Now what is delta EA? Delta EA is EA2 minus EA1 only. So that's why in the next step we have written it as delta EA. Now also A1 equals to A2, so this cancel out, and thus the K1 by K2 is coming to be e to the power delta EA divided by RT. Now here EA value is already given, delta EA value is already given, that is 5 into 10 to the power 3. So you just put the value here. You have to have a scientific calculator, calculate e to the power 2.02, and it is coming around 7.538. Since we need to round up to 2 decimal places, we are rounding up to 7.54. For reference, to know more about this rate kinetics as well as equilibrium, I have given two links or two courses. One is rate processes by Dr. M. Haldar of IIT Kharagpur, and also Dr. Amber Jain, whose course runs on chemical kinetics and transition state theory in NPTEL. So you can refer to these two NPTEL courses for getting more insights about chemical equilibrium and chemical kinetics. Thank you.